So in this particular function family, if you change the coefficient on the sine of pi x, what you'll notice is that you're not actually changing the amount of error. Notice the error in the upper right-hand corner is just remaining at 11 the whole time. Right? And so, as Brian correctly points out, what that means is that our equations are going to have a free variable in them, because this coefficient doesn't seem to have any power to affect the error. If you think of the error as a linear transformation, this variable is in the null space of that linear transformation. It's not affecting the error. So the only way to affect the error is to change the other variable. And you can kind of do that in such a way that it looks like the best we can do is right about there. 1.68, is that about what you had? Right, so in this example, when you set up the equations, you find out, so I'm going to just real quickly do that. My F matrix has the evaluations of our two basic functions at our data points whose x values were -2, 0, and 2. And at those points, the sine of pi x at x equals -2, 0, and 2 are all the same value, 0. And the evaluations of our other basis function, which is the constant function 1, is, again, 1 at every x value. And so this was the F matrix that they ended up with, so that when they did F transpose F, they got a matrix which did not have an inverse, 0, 0, 0, 3. So their system that they ended up needing to solve looked like this. C1, C2 equals, and I think it was 0, 5 on the other side. Right. So you look at this and say, this does not look like the kind of equation that has a consistent, that's a consistent system. But you'd be wrong. This has a solution. It just has too many solutions. The square matrix on the left-hand side is not invertible, but yet the vector on the right-hand side of this equation does belong to its column space. So we can actually solve this equation by looking at the second equation, 3c2 is equal to 5, and so c2 is equal to 5/3, or about 1.6666 repeating. That's real close to what we had right here, right? But c1 is a free variable. So c1 gets to be whatever it wants to be. So that means that the closest function in our family to this set of data has the form c1 times the sine of pi x plus 5/3. But then this c1 is allowed to roam free. So no matter what c1 I put there, I get a function which is exactly the same distance away from my points as all the others. So that's the first thing that could potentially go wrong. But don't let the non-invertibility of that matrix stop you. The system is still consistent, it just has a non-unique solution. The group that had the exponential model had to do an additional step along the way. And the reason for that is that if you plug in your data point into this model, and so here the model was y is equal to a times b to the x. Plugging in our three data points, my y values were, 1, 1, and 3. 1, 1, and 3. A times b to the x, a times b to the x, a times b to the x. And the b values were -2, 0, and 2. What I have here is not a system of linear equations. Right? A and B are not participating in linear equations over here on the left. There's no way to write that as a matrix equation. So unless we can do something to those three equations to make them linear, we're not going to be able to use the techniques of linear algebra to solve them. So what's the trick? What can we do to these equations to make it so that some versions of A and B are actually participating in linear equations instead of exponential? How do you turn exponential expressions into linear expressions? Logarithm. Take their logarithm. Exactly. So you get to choose the base, whatever you choose, just as long as you're consistent. But I'm going to choose a natural log. Let's just take the natural log on both sides of all three of these equations. I'll get the natural log of 1, 0. The natural log of 1, 0. So my new left-hand sides here are 0, 0, and log 3. And on the right-hand side, when I take the natural log of a times b to the -2, what I end up with is the natural log of A plus -2 times, -2 times the natural log of B. Right. There I'm just using the properties of logarithms. If I wanted to spell that out just a little bit more, b to the -2. First, using the property of logarithms that says that multiplication turns into addition. Multiplication on the inside is addition on the outside, so this is natural log of A plus the natural log of b to the -2. And then using the property that says that a power inside of a log is multiplication on the outside of the log. So that -2 just comes down on the front. Natural log of B. And I can do that same thing with my other equations here as well. Natural log of A plus 0 times natural log of B, and then natural log of A plus 2 times natural log of B. And so when I set up my system, what I end up with is as my right-hand vector 0, 0, log 3. And now the coefficients that I get here, -2, 0, 2, are no longer coefficients of A and B, but they're coefficients of natural log of A and natural log of B. So when I solve this system, my solutions are not the coefficients, but they're actually the natural logs of the coefficients that I was looking for. Right? But I've now made my system into a linear system, and we can go forward and use the tools of linear algebra to solve this. Just remembering that the solution of this, we then have to re-exponentiate to get our A and our B back out. So this is, I think, a proof of concept that even if your original family of functions does not form a vector space by itself, if you can transform your data in such a way that it does, we can still use this method to find the least square solution.